Hello and welcome to another video. In this video we're going to be doing another part of the advanced DSA topics, and we're going to be covering segment trees. And segment trees are probably one of the more difficult data structures. They're tougher to build than like heaps. Actually about around there, but I would definitely make sure that you know all the normal stuff like heaps, queues, stacks, all that kind of stuff, graphs, before you get into this one. This one's definitely a little bit less used and trickier. So let's figure out the use case for this. So let's say we have an array, and we have an array with these numbers, and these are the indices, and we are asked to get the sum. So you can get the sum. Segment trees also work for the maximum, minimum. There's a bunch of other stuff. But let's say you're asked to get the sum between two indices. So let's say you're given a query that's like, give me the sum between two indices, like 1 and 5, let's say. And let's say it includes these indices. So obviously the brute force thing is just go through the array and add up all of these, right? So for every single query you get, it would be O of n time, because we basically have to go through from the start to the end and add them up. Now there is a faster way of doing this, and this one's a pretty popular way to do it, and it's called prefix sums. And the way prefix sums works is we basically keep a total up to a certain index in a data structure, and then when we try to get the sum, it's going to be a lot easier. So the way it works is basically for the prefix sum, you just take whatever the previous number was, and then you add the current number in num. So the previous number here is nothing, so it would just be 0. Then you add the current number in nums. So this is 2, and this basically represents, this is the sum up until index 0, up until and including. So prefix sum for 1 would just be the old number for the prefixes plus the current number for nums, so that's going to be 6. Then the number here is going to be the old number plus the previous number here, so 9. Then we kind of keep doing this, right? So 15, old number 15 plus 9, it's going to be 24, 26. Basically the old one plus the number over here, 27, 29. And just to make sure, if we add all these up, so we get 6, 9, 15, 24, 26, 27, 29. That's correct. So now if we want to do this query, we just take whatever this prefix sum is at 5, so it's 26. And if we want to include 1, then we would subtract the 1 at 0, right? And that's basically saying, let's take this whole thing and let's subtract this section here. So then we are left with this part here, which makes sense, right? That's 1 through 5. So we'd say 26 minus 2. Now we get 24. So this allows us to get all of these queries in O of 1 time, right? Like no matter what query we get here, we can do these in O of 1 time. And that's good. But imagine now that we are allowed to change some of these numbers. So let's say I want to update number at 3 to something like 8. And then I want to do these queries again. Well, now the problem is all these sums are screwed up, right? So everything from here on is screwed up. These are all wrong. So I'm going to need to go and rebuild this prefix sum from this thing. So basically, when your data structure actually has updates, this prefix sums breaks. Also, the other way it would break, let's keep the old one, is if instead of asking for a sum, you are asked to get a maximum. So let's say I want to get the maximum between indices like 2 and 5 inclusive again. So you can't really store like a prefix maximum, right? Because how would you even do that, right? Like, let's say the maximum here is something. How would you say what's the maximum over here? And so on, right? It wouldn't really work. Because the problem is like, you could get like a prefix maximum. So actually you could do this. You could get like, what's the maximum in this range? But the problem is like, the maximum in this range, if you're trying to get an actual like, range that's not from the start, like if you're trying to get like this range or something, you can't just subtract 2 ranges, because the maximum in both of those ranges might actually be only in one side of it. So you can't just do like a basic subtraction. So for maximum, minimum, and also for sums and like differences, XORs, a bunch of other stuff, multiplying also works. With updates, you can't use prefix sums. So what we're going to need to do is we're going to need to build a segment tree. And what a segment tree allows us to do is we can update our numbers, right? So we can make updates, and we can query sum, maximum, minimum, all these things, with small changes to our data structure in of log n time, which is significantly faster than if you were to do a brute force of just going through everything. Right? So we can query in log n time, we can update in log n time, and we can build the whole tree in O of n time. So it's pretty fast to build, and it's pretty flexible where you can do a lot of updates. So now what we're going to do is we are going to actually show what it's going to look like. So we're going to show what it's going to look like, and then we are going to show the code. So let's go over how our segment tree is going to look. Our segment tree is going to consist of nodes. You can build this with an array, but it's easier with an object like a tree in LeetCode where you have left and right children, because it's not always going to be complete. So with an array, you basically have to have a bunch of empty indices. So we're going to use it building an object. It's going to be a lot easier. So our node is going to have a couple things. It's going to have, let's actually have it in blue. Okay, so our node is going to have a value, and it's going to have the range that it covers. So it'll have a left and a right for the range that it covers, and then it will have a left and a right child. So quickly looking at the code for it, it's going to look like something like this. It's going to have a value, left range, left child, and right child. So let's build this for this tree here. So we are going to have a root, right? Let's build in the middle, hopefully have enough space for everything. Our root, we're not going to put in value 0, we're just going to put in the range. So our range is going to be 0 to 7, right? Our root should cover the entire range. Let's actually write the range later in a different color so it's easier to see. Okay, so now we're going to have a left and a right child. So left, try to have a lot of space here. Left and a right child, and I believe we need 4 levels. So let's just draw out 4 levels, and then we're going to see how this works. So left and a right child again. Let's try to have some space. And then we can draw out our range afterwards. So now we have a left and a right child one more time. So left, right, right, left, right. Okay, there we go. Now we have a full tree. Now what we are going to do is we are going to actually write out our range. So our initial range is just going to be the whole thing. So it's going to be 0 to 7. Then what's going to happen is we're going to split our range in half for every branch. And if you have an uneven number, it's totally fine. Like if this was 0, 2, you would just have like 0, 1 on the left and 2 on the right. And that's why I said it's not always going to be complete. Like in this example, it's complete, but it's not always going to be complete. That's why it's easier with an object. Because if you're building like a tree, you don't really care if it's a complete tree if you're just using pointers, right? So our left range is going to be 0, 3, right? We're basically splitting in 2 every time until we hit a node where the left is equal to the right, and I'll kind of show that. So we have 4, 7 here. We split this in half again, so this is 0, 1, 2, 3. And now our base case is 0, 0. So instead of drawing like 0, 0, 1, 1, 2, 2, 3, 3, and so on, just know that the left equals right here, and I can even write that, left equals right. Just know that that is, and we'll just write down the indices here just so we can take up less space. So let's do this. We'll have this. There we go. So now we have a base case, and now let's draw the rest for these. So we're going to have 4, 5 here as the range, and 6, 7. And there we go. Now what you do is once you build up all of these, anytime you get to a leaf node, you just simply say, like, what's the value in the original array, right? So we're going to pass this array down to the constructor, and we're going to get these values. So it's 2, 4, 3, 6, 9, 2, 1, 2. So we can easily do that. Maybe let's write in this color. So 2, 4, 3, 6, 9, 2, 1, 2. And because this is a sum segment tree, the way it's going to work is the parent will just be the sum of the children. So this will be 6, 9, 11, 13, 15, 24, 39. Double check our sum. Did we do that right? Let's just double check. Maybe we did the prefix sum incorrectly. That could easily be the case. I think we did this a little bit incorrectly, so let's just double check. 2, 4, 9, 2, 1, 2, 11. Oh, this should be 3. Yeah, so a little mistake there. So 3, 14, and now 29. Now that is correct. Okay. So that's how you build it. You basically start with a root, you give it a range, you give it the range of the whole thing, and then you just keep recursing until you get children that the left is equal to the right. So let's look at the code real quick. So basically have an init, you make a root, and then we call this helper function called builder. We give it a range and the actual nums that are passed into the constructor. And it's pretty straightforward. So if left is right, you just return the node with left and right as the bounds, and the value is what it is in the array. Otherwise, let's get a midpoint and let's recurse left and right and let's add them up, because in this case, this is a sum segment tree, but I'll also show how to change a few things to make like a max segment tree or min segment tree, whatever you need. So builder, pretty straightforward. Now let's handle the next case where we want to update a value. So by the way, builder, we can write this on the top maybe. So build is an O of n. Now we have update. It's going to be of a log n. And the way it works is, let's say I wanted to update, I think what we had before was we tried to update this to 8. So we want to update range 3, or, like child 3 to 8. So the way it's going to work, pretty straightforward. You pass in the index, you start at the root, and you just traverse. And our base case is if the left and the right match the index exactly. Otherwise, we need to go left or right. So in the beginning, we're going to do the same thing where we're going to get a midpoint, and we'll say, okay, well, we got a midpoint. Is it in the left or the right? The midpoint range is going to be this. So we need to go left. Then here, we need to go right. Then here, we need to go right again. And then we have our base case, right, where here the left will equal the right. They'll both be 3, and this is the value we want to update. Now, pretty easy. You just update the value. So we want to update this to be an 8. And you return the value, and then you update the parents all the way up. So because the parent is the sum of the children, you would just update the parent all the way up. So this is 17, right? And then this is 31, I believe. Yeah. And it's pretty easy because every parent has access to the other child. So like, let's say I'm updating this parent. I have access to the other child's value. I can access it without recursing to it, right? I have a left pointer, so I can just check what it is. And then the right value got recursed up to me on the way up. Same thing here. I don't need to recurse all the way down here. I have the left child's value, so I can just take whatever I was given from the right child and then just go all the way up. You don't even need to actually do that. You don't even need to return here. You just update the value, and then for every parent you recurse up to, then you just say like, okay, its value is left plus right again, right? So you don't even need to return the value. So that's how you do an update, and let's take a look at the code. So we have an update. We're going to have this update helper function. And basically, it's just going to say, okay, all we need to do is update one of them, right? So if we have the base case, let's update it and let's return. Otherwise, let's just go wherever we need to go, and then let's just get the node's value. So we don't even need to actually return. No, I think the way I think here I did return the node's value, but you don't really even need to do that. You can just recurse left, update the value, right, and then just update the node's value, and it's totally fine. So you can do it a bunch of ways here, but pretty straightforward the way I explained it of how to code it up. So let's go to the next part. And this is the part that's going to be tricky. So we have our update. Now, the next part we need, that's going to be the whole point of this, is the range query, right? We want to get the sum of a range, or the max of a range, or the min of a range, or something. This is going to be in O of log n, right? So it's kind of like a compromise between the prefix sums and the brute force, but this lets us make updates where with the prefix sums we couldn't update anything. Also, this works for like maxes and mins, and obviously prefixes does not. So this works for more things. So let's say we want to get, I think our original thing was like the range of 1 to 5, right? We want to get the sum of numbers 1 to 5. How do we do that in log n? So the way it's going to work is our range query will have 3 cases, and this will make a lot more sense once we start going into it. So one case is whatever node we are in and range have no intersection. So for example, let's say our range is 1, 5, and we happen to be in node like 6, 7 or something. So this has no intersection, right? There's nothing in common here. So here you would return depending on what you're looking for. So if you're looking for a sum, you'd return 0. If you're looking for a maximum, you'd return like negative infinity. Return something that doesn't change all your other stuff, basically. Okay, now we have our second case. So Our second case is our node is in our range completely. And it's not the other way around, it has to be this way. So let's say our node is 3, 5 or something. So now this node would be in this range completely, right? Every single value in the node, 3, 4, and 5 are also in this range. So if that's the case, let's return the node value. And finally, we have some intersection, but not complete. So let's actually scroll down here a bit. So there we go. So we have some intersection, but not complete. Then we recurse to both children. And when we recurse to both children, we're going to keep, so before we took like a midpoint and stuff, now we don't even need to do that. We'll just recurse to both children and keep the range we're looking for exactly the same. And these 3 cases will handle everything for us. And it'll kind of make sense once I go through this example. So let's say we're looking for 1, 5. So originally we looked for 1, 5 in here. And we say, okay, well, they do have an intersection, but obviously our node is not in here. This is in our node, but like I said, you can't have the reverse. So our node is not in here, but there's an intersection, so we're going to go to case 3. So case 3 means recurse both ways. So let's actually maybe use brown here. So we're going to recurse here and here. Let's do the left side first. So 0, 3, and 1, 5. They do have an intersection, but the node isn't completely in here, right? Because like 0 isn't in here. So we have to recurse both ways again. So let's recurse both ways. 0, 1, there is an intersection, but they are not, this is not completely in here because 0 is not. So we'll recurse both ways. Now 0 is completely not in here. Right? So if 0 is completely not in here, we want to return 0 up here. 1 is completely in here, so we wanted to return whatever the value is, so we'll return 4. So this node has 0 and 4, and now when we recurse back up, because it's a sum, we return the 2 values that we recurse down into combined, right? So we'll return 4 up here. So we will return 4. Now let's do this side. So 2, 3 is completely in this 1, 5, right? So if it's completely in here, we don't need to recurse, we can just return its value straight away. So we will return 11. So our left side up here returned 11, our right side, or our left side returned 4, our right side returned 11. So now we will return the total of both of the recursions, which is 15. So we'll return 15 up here. Now let's do the right side. So we have 4, 7. There is an intersection, but it's not complete. So let's recurse both ways. 4, 5 is completely in here. So then we can just return its value straight away. We don't need to recurse anymore. So we'll return 11. 6, 7 is completely not intersecting with this. So we will return 0. There's no intersection, and we're looking for some, so we'll just return 0. So here we'll return 11 plus 0, so we'll return 11. So now our total should be 26, right? 15 plus 1. So let's double check that. This is what it is. So we have 7 plus 8, which is 15, plus 11, which is 26. So that is correct. Right. And the reason why this is log n is because you will only recurse all the way down to a leaf to 2 leaves. So here we did technically recurse to 3 leaves, but basically this didn't really this only costs us 1 more operation because we were already basically there, right? So the leaves we're going to recurse to are the 1 and the 5. So we're going to recurse down to here and down to here. We did recurse down to the 0 in this case, like I said, but this was only 1 operation, so this isn't going to hurt our complexity. So we're basically going to recurse down 2 full paths. And then the rest of it we will break early. And as the tree gets bigger, you won't have to recurse down as far because you'll just have like huge range chunks that you'll just be returning. So that's why it's log n, because you're recursing down 2 full paths in a pretty balanced tree. So then that would be like 2 times log n, which is just log n. So now that we know how to do the range query, let's take a look at the code for range query. And here it is. So we're going to call the query helper on the range that we want. And the query helper is pretty straightforward. We have our 3 cases, right? So this is our 3 cases where if the node is completely in the query, this is if there is no intersection at all, and this is if there is an intersection but not complete, then we just recurse down both and we pass in the old range. So this is what you'd have to change to do like a min and a max. So now let's take a look at the full code. And let's see how we can change it for a maximum. So we have our node, we have like our build, and I'll provide the code as well. So basically all we have to do is anytime we do a sum, we just change that to maximum. And we can even, we'll do an example of a maximum query as well. Not with code, but just in the picture. So basically, whenever we return a node that's like left plus right, instead of this, we would just return max left right. And same thing in the update. Whenever you update a leaf node, instead of updating up the parent, where the parent is the left plus the right, you would just say the parent is the left, the max of the left and the right. And the query is the same thing. Instead of passing in the plus for the left and the right here, you would just update to max. And that's pretty much it. And also instead of returning 0, because this was a sum, we would return like negative infinity or something. So you literally make like 4 or 5 updates in your code. And let's go back to our picture and show what this would look like if we are looking for a maximum. So let's do this exact thing with a maximum now instead of a sum. So we're going to have the same kind of tree, but all we're going to look for is a maximum. And I'll kind of, we will have to update it a little bit. So let's actually see where, I think this is good from here. So let's change these values to make it a maximum tree. So let's say we are filling this out, right? We filled out our leaf nodes. And how would we do a maximum? So for the initial nodes, it's pretty straightforward. You just take the maximum, right? So here would be like 4, 8, 9, 2, 8, 9, 9. And that makes sense because 9 is the biggest. So notice how if we want to get a maximum, it's kind of the same thing. We're not recursing all the way down. We're not going through every single value. So if we get to a range that completely covers our query, we can still return right away. So it's going to be the same. It's going to be the same time complexity. So let's do the same query of 1, 5, or maybe let's do another one. Let's do like 2, 5 or something. So let's do the max. Let's write this down. Max of 2, 5. So this should be 9. Actually, let's do a max that doesn't include the 9. Maybe that'll be better. Okay, so let's do a max that doesn't include 9. Let's do like 5, 7 or something. There we go. So we should get a 2 here. So our range is 5, 7. And let's walk through it with the recursion. So 5, 7. First, there is an overlap, but the node, remember our 3 rules, the node is not in this range. It's not completely in this range. In fact, this range isn't the node, so we'd have to recurse both ways. Okay. So 0, 3 is completely disjoint with this. So because we're doing a maximum, we want to return a value that we're never going to use. So we'll just return like negative infinity. So we can return negative infinity here. Now 4, 7 is completely in here. Is it? No, it's not. Okay, I was going to say because it shouldn't be 9. So 4, 7 is not completely in here. So 4, 7, there is an overlap, but it's not complete. So we need to recurse left and right. Okay. Now let's do 4, 5. 4, 5, there is an overlap, right? But it's not complete. So we have to recurse both ways. So 4 is not in here at all. So we will return negative infinity. 5 is completely in here, so we'll just return the value. So we'll just return 2. Now let's recurse up here. So we got negative infinity and 2. The maximum there is 2. So 2. Now 6, 7. There is an overlap, but it's not complete. Actually, no, it is complete, right? Yeah. 6, 7 is completely in here. So we can just return the value. So we'll just return 2. So we return 2 and 2. So here we would return 2. And then here we got negative infinity and 2. And the maximum of that is 2. So notice we got exactly what we were looking for. So maximum and sum and minimum, if we go back to the code one more time, very easy, small updates, right? Instead of having a plus here, you have a maximum here. Instead of having a plus, basically everywhere you have a plus, you have a maximum. And also for this condition here, where there's no overlap at all, just change it to whatever you want. So if you're doing a maximum, return negative infinity, because returning 0 is not going to be great, right? Let's say all your numbers are negative, then it's going to screw up your solution. That's literally it. You can literally say like take every plus sign in this code and just change it to a maximum, and that would give you exactly what you want. And there's like 4 or 5 of them. So I'll also provide the code for the sum tree. And yeah, I think that covers everything I needed to cover. So this is going to be used in hard problems. So now, like in this Alice and Bob problem that I did earlier, where you're asked to get a maximum in like a binary search kind of way, now you can do it this way, where you couldn't do a linear search, but you can do it like this. And you will also be asked, I think I did another problem before where you are asked to do this like range sum query where your numbers keep changing. So now you know exactly like what type of problem to do it on. It's going to work perfectly on an array where you update numbers and you're looking for a minimum, maximum, multiply would work. Just think of things like that, right? Minimum, maximum, multiply, subtract, XOR. There's like a few. I think like GCD and LCM also work. So there's quite a few of these cases, and this data structure is basically not covered on LeetCode. So just wanted to introduce this one to you guys. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.